So a sphere with a 1.4 centimeter in diameter is placed in a free stream of 18 meter per second at 20 degrees Celsius and 1 atm. Compute the diameter Reynolds number of the sphere if the fluid is air, water, and the hydrogen. So we have a gas, and then a common gas, air, common liquid, which is water, and we have a very specific gas here. So this is the answer. It might be a simple question, but what you need to understand is you need to make sure that you choose the right equation, and you choose the right range. It might be simple for you to remember the Reynolds number equation, but at least you must know the situation. So in this situation, we will use rho Vd over mu, and we substitute all the value here, then you could get the value of Reynolds number. So, and then as I said, you must know the type of flow, the situation, the condition of that flow, and then you need to know what kind of range that you need to choose. So in this situation, so we have a sphere here. So, and then this is a solid object, and then you have a fluid free stream here, and then you need to calculate the Reynolds number. So in this situation, because what we have here is actually the sphere, so it is okay for us to take the diameter of this sphere. Okay, so now the equation will become rho Vd over mu. Okay, if the object that we have is actually a flat plate like this, okay, because the flat plate here will not have the diameter, it is okay for us to take the length of this plate. So, and then here might be the equation will change into rho VL over mu. So, however, okay, so in flow in pipe, for example, we have a flow in pipe. So we have a pipe here, and then we have a full of water inside this pipe. So the Reynolds number is calculated by the equation of rho Vd over mu. Okay, might be the same equation with what we calculated for this sphere. However, the range is different because in this situation, it is about the flow in pipe. The flow in pipe, so it range about the turbulent is flow that Reynolds number more than 4,000. Okay. However, for this condition, because it is the situation where the flow is around a bluff body, so might be we need to use the range of, if the Reynolds number is greater than 5 times 10 by the power of 5, then we could assume that the flow is 100% turbulent. Okay, so means that sometimes we need, the equation is still the same, but you need to know what type of condition of that flow is flowing. Okay. So, and then, okay, so the second slide is actually discussing about the hydrogen here. So, as we know, okay, so it might be, this is the very simple calculation. So we use the velocity, which is 18 meter per second, and then we use the mu, the dynamic viscosity of the hydrogen. So we have this number 2,333. However, we know that the viscosity of gas is easy to change. It is affected with temperature and pressure. And for example, we are focusing on hydrogen. Why I bring these matters up? Because you are going to conduct your master project, and might be you further your study for PhD and so on. So you need alert that the properties that written in textbook is actually for the general purpose. So it might be sometime not suitable if you take that parameter in your research, because in your research you will need a very specific numbers to calculate to be substitute in your works. Okay, for example, we have hydrogen here, and we know that the hydrogen has its own molecular weight of 2.012. So it is okay for you to take it as 2. So, and then you know that gas is very sensitive. Just a few degrees Celsius temperatures change could expand the volume and so on and so forth. So it could create a very totally different value. So it might be for this Reynolds number, might be you need to calculate like this. So for example, we start to calculate the constant for gas. So we use 8,313 over its molecular weight. So we divide by 2.016. So we get the 4,100 here. And then we start to calculate to estimate its specific density, its density on that situation. So, and then we use the idea of P over RT. So, and then the P, it might be the atmospheric pressure. Okay, so, and then we have the R, we have the temperature there, and then we got the density. And then we try to estimate, because in Reynolds number equation, we have dynamic viscosity. So we could estimate the changes of viscosity of hydrogen here by having this kind of equation. So you may have this equation in textbook, in the viscous fluid flow textbooks. So, and then the N here is actually the specific number that we need to get from the table 1.2. You could refer your textbook, and also I think I already upload the table for this chapter in my website. So, and then we substitute all the value, we could get that the mu naught here is actually the representative or the reference value of dynamic viscosity for hydrogen. So, and then if we substitute the value, we could get, okay, so this is the table that you could get from the textbooks. So, and then we could get the hydrogen here is 0.68. That's why we take the N here is 0.68. So, and then if we substitute all this value, we could get that mu is equal to 8.411 by times 10 by the power of minus 6. And then we use this dynamic viscosity into the Reynolds number equation. Then we could calculate very specific Reynolds number at that temperature, which is equal to 2,393. So the Reynolds number is dimensionless, so please do not put any dimension, any units at the back of your Reynolds number. Okay, is that okay? Could you get the notes? Yes.
So why both have different answer in first and second method for hydrogen?
Okay, so it is because here we are using value of dynamic viscosity in textbooks. But it is very common value of hydrogen. Okay, mu is dynamic viscosity, and normally this term, this number is taken from textbook. So textbook is a general or the representative for hydrogen. Might be it takes for example, 20 degrees in minus 10 degrees Celsius, for example, or might be in 0 degrees Celsius. Okay, but might be your question is now you are calculating hydrogen at 20 degrees Celsius. So means that you need to calculate the specific value for the dynamic viscosity. Okay, please try to open your textbook and then find what is the representative value of dynamic viscosity for hydrogen. So this is the first calculation. So we just use a common numbers, a common value for dynamic viscosity for hydrogen. However, for the second method here, we are very specific because we are very alert. Because normally, for example, hydrogen is 2. We take the molecular weight for hydrogen is 2. But now we take, it's very specific, we take as 2.016, and then we calculate the density changes. Because gas is very sensitive, you just give only a few degrees Celsius, it will expand. So, and then here we estimate the dynamic viscosity, okay, by using this equation, and then we could calculate the final Reynolds number is 2,393.
Okay.
Okay, so we just want to show you, it is, we have a specific method to get the specific value, because in master level might be you need to you need to do research with a very specific condition, so you need to calculate with the specific value also. Okay, can you get the screen, print screen, the image? Okay, so we go for the second question. So the question is actually finished until this one. So let's say a telephone wire, 8 millimeter in diameter, is subjected to a cross-flow wind and begins to shed vortices. Okay, from figure, okay, I will, the next page is the figure. From figure, what wind velocity in meter per second will cause the wire to sink at middle C? Okay, so so this question might be tricky. So we left about the tricks here. So the middle C is actually the common frequency for musician. So it can be seeing the frequency that might be start to give a frequency with a little bit high pitch. So people start to notice that voice, that sound. So, or it is equal to 256 hertz. Okay, I just give you the 256 hertz. Okay, here what you need to know from this question is sometimes in master level you need to know certain dimensionless parameter that suitable for that situation. Okay, because in undergraduate might be we always use Reynolds number in fluid flow, but actually not all the situation can be used Reynolds number. So for example, in open channel, so we are using Froude number, and if we are doing something that vibrate, so that we have something like a resonance. So because when we have a diameter, a wire here and a cross wind, so they start a resonance, and the wires start to vibrate. Okay, so we will use the number of Strohal number. So this is not I just take this example because it is not familiar, not common for us to evaluate with the Strohal number. So the explanation is here. You could read by yourself. So the equation for Strohal number is ST, the symbol for Strohal number, and it is equal to F times L over U, or F times D over U. So again here, you need very careful because, okay, the situation is something like this. Okay, for example, we have so in your country, for example, you have electrical poles like this. So, and then when the crosswind comes, okay, so it will create this line vibrate at certain frequency. So, and then might be when the wind become faster and faster, so it will create noise. So, and then we need to alert about when we want to use L and when we want to use D. So in this situation, because the wire here, the cross section of the wire is actually in circular, so we have so we take the diameter of this wire as our constant. So we take the diameter instead of the length, because if we have a wire hanging like this from one pole to another pole, so and then we find that the most influence parameter is actually the thickness of the wire. So the thickness of the wire means the diameter of the wire instead of the length of the wire. So that's why in here we take the diameter here as our main parameter. So and then from the textbook we could get that for sphere in uniform flow, the Reynolds number range between 8 times 10 by the power of 2 and 2 times 10 by the power of 5. They coexist two value of the Strohan number. The lower frequency is attributed to the large scale instability of the wake and is independent to the Reynolds number and is approximately equal to 0.2. The higher frequency Strohan number is caused by small scale instabilities from the separation of the shear layer. So here we take the 0.2 because, okay, so this is in your textbook, they were told that the Strohan number 0.2 is might be the turning point. So the turning point when the resonance is become higher and higher. So this is the Reynolds number. So its Reynolds number at this moment will reflect about the frequency, the velocity of the wind. And then the calculation is quite easy. So we have the Strohan number, which is 0.2, and then we substitute all the value. We could get that the U is equal to 10.24 meter per second. And then we could calculate the Reynolds number, which is equal to 5,461. Okay, so we move to the question 1.3. So let's say if we have wire stated in problem 1.2 and the cross wind is now about 12 meter per second, and then we need to calculate the drag force, okay, by estimating by use this figure. Means this figure is showing the drag coefficient of a circular cylinder. So the answer is like this. So first, I think you still remember to the calculation, the equation to calculate the drag force. So the common one is CD times 1 over 2 rho AV square, which is the CD here is the drag coefficient. So in this situation, might be we have all the parameter here. We know the rho, the density of the fluid, A is the cross-sectional of that object, and the V is the velocity of that fluid. So the main problem here, it might be the drag coefficient for that object, for that situation. So here the hidden message that I want to tell you here is sometimes I hope you have you could get value, or you could read the coefficient from any tables, because according to my experience working in industry about 1 year, so sometimes we need to calculate something by looking with the proper handbook. So handbook, there is a lot of tables there, so you need to choose which one is the correct table to be referred, and then you know how to take a certain value from that tables. So for example, we have tables, we have chart here. So yeah, we could see that on the left side here, the y-axis is showing the drag coefficient, and then the drag coefficient is now changing according to the Reynolds number. So means for this situation, we need to know first the Reynolds number. So we could calculate the Reynolds number, so we get it is around 6,400. So, and then according to this one, we could say that the value of 6,400 Reynolds number will give 1.1. So, and then again, please be careful, but sometimes in a table or in a chart, they will give you in terms of scale log scale like this. So this is 1, this is 10, and this is 100, and this is 1000, and this is 10,000. So this 6,000 is might be something here. So I just estimate this might be around 1.1 or 1.0. So it's okay for you. So I just take the CD is 1.1. So and then I substitute in the equation. So we have half here, we have row A and V. So and then we could calculate it is the drag force is 0.76 Newton per unit meter. So again, please make sure that you know what is the physical meaning of the per unit meter here. So in this situation, okay, because we are calculating about the singing wire, means we have a pole here, and then we have a wire there, and then we have a flow like this. So if we enlarge this image, might be we could draw something like, okay, might be we could okay, we have a very large cylinder wire here. Okay, you just imagine it is cylinder in shape. So and then we have a flow here. Okay, and then the A here is actually the cross-sectional area. So the cross-sectional area from wire here can be taken as, okay, we know the wire is cylinder, so we have a wind flow here. So it is equal to the projection area. So the projection area means, so projection area means for the shadow of this wire. So the shadow of this wire is can be reflect as if you have a cylinder here. So the shadow will be in rectangular shape. So the area here must be rectangular area. However, in this calculation, the diameter, which is the height of this shadow, is equal to 0.08, 0.008, but we take length of this wire is equal to 1. So that's why we multiply with 1. Then our answer will give per unit meter. So mean for every 1 meter length of wire, they will give you 0.76 Newton of drag force. So mean if the length is might be 10 meters, means that the drag force is 0.76 times 10. So this is the common unit in engineering. I think you already you have experience about this. So if we are calculating about the friction and so on and so forth, for example, the resistance, so sometimes they will give you in per unit meter. So mean you could multiply by yourself what is the total drag force for that system. So I just erase everything so you have a very clean notes here. Okay, next. So we have this situation. So this is closely related to the idea of viscosity. Okay, so for example, we have one situation of this for flow in pipes. So we have for oil flow in a pipe far downstream of the entrance, figure 110 and 111 from in your textbooks. The axial velocity profile is a function of r only and is given by u equal c over mu r square minus r square. So where c is the constant, and r is the pipe radius. Okay, here. And then suppose the pipe 1 centimeter in diameter and u max is 30 meter per second. Compute the wall shear stress in Pascal if mu is equal 0.3 kilogram per meter second. Okay, so first what you need to understand about downstream, the entrance here is, okay, if you read a textbook about flow in pipes, okay, you will know that if you have a pipe here, okay, so at the point here, so we have one condition which is called the no slip condition. So mean the molecule here will stay at certain will stick very hard on the surface, and the velocity is 0, and then it will create velocity distribution. Okay. However, at the entrance, okay, at the entrance, there is a transition region, because from here, the velocity, it might be almost uniform because there are no resistance at the edge here. So once it's entered the pipe, so it start to feel the resistance. Okay, that's why they will create, okay, because you know, the molecule here might be immediately stopped because the no slip condition. Okay, because they will stick very hard on the surface, and then but the center molecule here will flow at its maximum velocity. So it might be some creates certain kind of this, like this one, for this one. So it is closely related to the idea of boundary layer, because if it is state here, okay, so there is a molecule that resists the fluid motion here, okay, until at certain length. So this is the transition between the entrance of a pipe and what happened for the average pipe. So this is okay. So sometimes in your, if you do the simulation, of you do the calculation, we in a very specific calculation, so they will take care about the entrance phenomenon here. But for normal calculation, we could ignore what happened in the entrance. So this is what it's mean by pipe far downstream of the entrance, because they want to neglect the development of velocity profile at the entrance. Okay, so here we will learn in chapter 4, 5, and 6. There is, we call it a laminar boundary layer here, and then we have a turbulent boundary layer here. Okay, so that's another story. So, so this is the idea. And then I hope you could understand the meaning of small u here. So it is the velocity for every molecule here. Okay, so means that each, okay, I try to erase everything here. Okay, so if we enlarge this place, this section, we could say that actually the velocity distribution is like this. So it is a no slip condition where the molecule is the velocity is 0, and then the velocity is increase and increase and increase until it reach its maximum value. So the velocity for each location here is represent as small u. Okay, small u here. And the average velocity, it's always stated show as capital U. Okay. Okay, so this is the, I hope you can understand this one. Okay. So this is the experimental about the velocity distribution inside the pipe. So okay, so from this question, what you need to know is, I hope you could derive an equation from that situation, and then you could feed in the equation. So for example, okay, we know that the velocity, at certain height, at certain location is given by this equation. U is equal C over mu R square minus R2. So, and then C here is the constant. And first we need to calculate what is the value of that constant. So it is something like we need to find a constant for a graph, for a function. So what we need to do is we give certain coordinate, or we give certain value that related on that line. So what we could do is we know that U max is occur at R equal to 0. So where R equal to 0 is, so you know that we have a pipe here, and we learn about the coordinates. We know about the cylindrical coordinates or polar coordinates. So we are taking care about the R here. Okay, and then because the velocity distribution will create something like this, so the middle point is the highest one. So we could say at this point, which is the R equal to 0, so the U will is the maximum value. So we substitute the value here, the R equal to 0, and then the value of U is now become the maximum value. We substitute into 30, and then we could get that the constant is about 3.6 times 10 by the power of 5. And then, so you know that U max is C over mu R square, because small r here is equal to 0, and then we calculate the du d max over dr, we could get it is 2cr over mu. So why we calculated this one? Because we want to estimate the shear stress at the wall. So the shear stress, okay, in previous notes, we discussed about the shear stress, so we could write as tau equal mu du dy. So previously, the common linear motion, we could write tau is equal mu du dy. Okay, however, in this situation, because we are dealing with a circular shape, so we change the value here, the dy value here with dr. So, and then it can be calculated as mu du max over dr at y, or at r equal to capital R. Okay, why we take R to capital R? Because if you see previous notes, might be in certain solution, you could get that du dy here always take y equal to 0. But suddenly in this situation, we take R equal to R. So you must know that why we take y equal to 0, because in flat plate like this, okay, the velocity distribution might be can be drawn like this one. So the highest shear stress is occur when y equal to 0. But for this situation, we have a circular pipe like this, and then at r equal to 0, it is a maximum velocity. The shear stress maximum occur when the value of r here is at the wall of the pipe. So here the value is small r is equal to capital R. So, and then we substitute this one because this is the rule. Might be you say, oh, it's quite weird when you take velocity at r equal to 0, but r here is the maximum r. Okay, so this is the, because if you see the du dy here, okay, from the another perspective, we could say that it is about the difference of u and y. So mean the u here is the lowest velocity, the highest velocity minus with the lowest velocity, and y here is also the gap of that system. Okay, so we substitute all of that, okay, and then we could say that the tau here is actually 2c and r, and then we could calculate the tau here is by using this equation. We substitute this one, we get it is around 3,600 Pascal. So again here, might be the name is shear stress, but actually it gives you the physical meaning about pressure. That's why the force is equal to tau times A. So it is equal to force equal to pressure times A. And then we could calculate the Reynolds number here because the situation is the flow in pipes. Okay, so then we use the rho Vd over mu, we substitute everything here, so and then we get it is around 900. So we could assume, because this is the flow in pipe, so the flow pattern, the flow type is a laminar flow. Okay, any question until this question?
No, Doctor, clear.
Okay, so can you take the notes, because I will not upload the PDF notes.
Yes,
Okay.
Doctor, I'm writing my notes.
Okay. Okay, and then we continue with this one. Okay, for example, we have a tornado. Maybe can be simulated as two-part circulating flow in cylindrical coordinates. So the idea it's okay. We learn about this in polar coordinates. So it can be reflecting about the rotating around flow around rotating cylinder, because you know tornado is a rotating flow. Okay, so might be so the equation must have vortex. Okay, to simulate this one, might be we could simplify it as VR and Vz is equal to 0. It is just to simplify our calculation, just to give you might be a very simple pictures, simple idea how to use, how we could use what we learn in ideal flow, in flow around cylinder and so on and so forth in real situation. So actually, if you really want to analyze this one, you need to take care about VR and Vz, because in actual, if we have axis here, the tornado might be rotate, okay, become bigger and bigger and so on and so forth. So means that why the shape of tornado is become bigger and bigger, because for sure it has value of VR. That's why the molecule here will increase itself, because it has velocity in VR direction. Okay, however, in this situation, we just to simplify the calculation, might be we just assume that all this molecule is turned around on its own path. So that's why it only has the value of v theta, mean the value of tangential value here, v theta. You may refer to the cylindrical or polar coordinates. So, and then a molecule at here, there are no VR, mean there are no velocity according to the radial axis, and also there are no Vz. Vz here is this axis. Okay, so this is just to simplify the calculation here. And then in this note, okay, it says that it can be simulated as two-part. Two-part means the V naught range here can be calculated with two different equations, depends on the value of R. Okay, why? Because normally if you are calculated in common engineering problems, might be we use only one equation, because the vortex is not too high. But tornado, as you know, it can lift house, roof, for example, and so on. So mean the velocity is very high. So according to these textbooks, so it will give you range for this one to calculate the V theta equal to R omega of V theta is omega R square over R. Okay. So, and then we need to calculate to determine the vorticity and also the strain rate in each part of the flow. Okay, so I think about the vorticity here, you already know, because we already discussed this one previously. So it's show as zeta. In some textbook, they will just use the alphabet of Z, okay, because these Roman symbol is not 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 easy to write on paper. So and then the vorticity here for polar coordinate can be written like this one. So and then in vorticity only u theta has a value, so means we could neglect the existence of ur. So now we only evaluate about these two parameters. So and then for r equal or less than capital R, so we take the idea of v theta is equal r omega, and then we substitute the value of r omega, and then we found that the vorticity is about 2 omega. And then if the r is bigger than r, the v naught is the omega r square over r, and then we substitute in the equation, so we get the vorticity is equal to 0. So actually this question, okay, what is the meaning of r is bigger than capital R? So means that actually the when the region, okay, means that outside the tornado is actually there are no force to there are no flow, or maybe we could say that it is a very flow rotating flow. So it is something like this. So for example, we have a tornado here. So this is the axis. So we have a tornado here. So you know that inside the tornado, this is the R, the capital R. So this is the shape of the tornado, for example. So now when the R is bigger than capital R, so meaning you are evaluating that here. So at this region, there are no forces to spin you according to the wind. Okay, so means that the vorticity means the capability of that fluid to move in circular motion. So as I said previously in our lecture, so some textbook they will use a certain symbol, because if you see the Navier-Stokes equation and so on and so forth, they will write in certain form. So I hope you could know that clearly. For example, in some textbook, they will write the vorticity is 1 over r del r for r and u theta. And you know the symbol of del and del r will represent the partial differential. So it's, you can say that I need to constant the value of u theta. So we constant it, and then we differentiate the value of r. So we have dr here, and 1 over r is constant, and then we constant the value of r, so we have an r here, and then we differentiate with u theta, and then finally you will get this value. Okay, in some textbook they will give you as u prime and v prime. So please be careful when you do revision from other textbooks. Sometimes they will give you in another form, but it's not the wrong equation. And about the strain rate and so on and so forth, so you could refer our textbooks. So strain rate, for example, the epsilon here is the strain, and we put a dot here. Okay, so it's will reflect the strain rate. So the equation is here, and if you substitute all the value, you can get the value of the equation of the strain rate here. And then we substitute with the range here for r less than r and r greater than r. So you could get each value. Okay, so maybe I'm not so familiar with the calculation of strain rate for fluid here. So, but to answer that the question, so this is the answer. Okay, now we move to question 1.7. So let's say we have a two-dimensional unsteady flow that has a velocity component as stated here. So we have a u equal x over 1 plus t, and v equal y over 1 plus 2t. And then the question is, find the equation of streamline of this flow which pass through the point x0, 1, 0 at time t equal to 0. So the idea here is, okay, as I said previously, okay, the idea of streamline here is we try to give mathematical equation for the flow. So for example, if you have at the real situation, we have a flow like this. So what we need to do is we need to make sure we need to create a mathematical equation that could reflect or could show the path of that flow. So that is the streamline. So as I tell you previously, so we could compare the experimental work for streamline with the calculation work. Okay, so the experimental work can be done by using the wind tunnel and the smoke generator. Okay, however, if we have flow, if we have moving fluid, it is not easy to show them as a line unless you are using ink in water tunnel, for example, or you use smoke generator in a wind tunnel. Another idea to know what is the streamline is we get the value of velocity at each point. So how to get the velocity at each point here? First, might be you can use in experimental way, might be you could use the anemometer, or you can tap the pressure, then you could do calculation, because in streamline, okay, you could use the idea of Bernoulli equation. We have P over rho G, V square over 2G, and Z. And then if we know the pressure, okay, let's say we assume that the Z is not influenced at all. So we could neglect the value of Z, the height. So, and then we have pressure and we have velocity. So then when you could get the pressure, you could calculate what is the velocity for that point actually. Okay, there are so many ways to find them. Okay, so the idea is, okay, certain scientists will take the value of velocity. That's because the idea of streamline here in simulation work. So let's say in ideal flow that we revised last week. So we have one set of equation which called Cauchy-Riemann equation. So in Cauchy-Riemann equation, the equation is start with u. Mean the subject of that equation is the velocity. U is equal d psi over dy and so on and so forth. So means that the idea is we get the velocity first, then we create equation for the streamline. And then we compare the streamline from our calculation with the real streamline that we get from the smoke generator to make sure to validate whether our equation is correct or not. Okay, that's the idea. That's why in this equation, in this question, they will give you equation for velocity. It gives you in x direction and also in y direction, because we are assumed if we have a very in flow in pipe, for example, so the molecule will flow might be at this axis and also at this axis. Okay. So that's why in this question, they just give you the velocity equation, and our idea is to create the stream function. Okay, so I just use the idea from that textbook. So previously what I give you, the derivation of psi here. So in V here, I use the minus d psi over dx. But according to our textbook, viscous fluid flow, they neglect the negative sign. So it is okay. So the difference is we just, we could get the streamline, but might be it is difficult for us to know which direction it is, whether it is flow from right to left or left to the right. That's it. So, but the stream function is the same. So, and then because it has u and v here, so and then we could say that we, we are aiming to get the value of the psi. So, and then we could rearrange this equation become the psi u times dy and v times dx. So, and then we equalize these both equations. So we have u times dy and v times dx, and it also can be rearranged as dy over v and dx over u. We just bring the parameter to the left and right hand side. So, and then we know the value of u and v. So we substitute the value and then we rearrange this one. And then you know that because we have dy and dx here, and to eliminate the value of dy and dx, what we need to do is we need to integrate both sides. So we integrate both sides here. And then because it is integration is for y and this integration is only for x, so we could do something like this. Okay, so we have 1 over y here, so integrate as ln y, and we have 1 over x, so we have the ln x here, and it is okay for us just to give one constant at the right hand side here. And then we rearrange this one, and then we could say that the value of y is actually the constant times x by the power of 1 plus t over 1 plus 2t. So we label this equation as equation number 1. So, and then because the question says that this streamline is going through point x0 and y0. So what we need, I think you have experience, if you have unknown equation, so we could fulfill all the parameter in that equation if we know the location, the coordinates that go through the line. So we have x0, y0. So we substitute the value, we could get the value of c. Now this is the value of c. And then we substitute to the previous equation, equation 1, and then we substitute the value of c, and finally we could get these terms.